All right, guys, here we go. Note A, transformation of sinusoids. Just like I told you that we're going to work on transformations first from our algebra days. This in the beginning, I mean, it's not really like a lesson. It's kind of more like an overview of like kind of seeing like some facts here. This is from the 1970 AP Calculus exam. Your parents probably weren't even born yet. Uh, Obviously, the Cal exam is not like this anymore, but so here it is. We're just gonna. This is like your original. And the first thing I'm going to do, guys, is I'm going to make a table here. So I'm going to say x, and I'm going to call it f of x. And I can see that I have everywhere from -3. So I'm using these points here. -3, -2, -1, 0, 1, 2, 3. I was mentioning the x coordinates. -3, -2, -1, 0, 1, 2, 3. So this means f of -3. F of -3 is -3. Does everyone see how I got that? This point right here is -3 comma -3. So that means f of -3 equals -3. And it's like that for the first three of them, I guess. This is f of -2, which is just -2 from this coordinate right here. This is f of -1, which is just -1. And then we get to the more fun ones. This is f of 0, which is -1. See? That point there is 0, -1, which is f of 0 is -1. F of 1, which is 0. And f of 2, which is 1. And then f of 3, which is 0. Have I confused anyone? Everything pretty straightforward, right? Okay. Based off of that, we're going to plot these. So this one says that my new y's are the absolute value of f of x's. So I'm going to write x, absolute value of f of x. And I'm going to go the same values, -3, -2, -1, 0, 1, 2, 3. Absolute value of f of -3, which happens to be absolute value of -3, which is just going to be 3. So -3, 3 points. -3, 3. Absolute value of f of -2, which is just going to be absolute value of -2, so 2. So -2, 2. Absolute value f of -1, which is absolute value of -1, so 1. So -1, 1. F of 0, absolute value of f of 0, which is just absolute value of -1, which is 1 again. So 0, 1. In case you can't tell what's absolute value, this is absolute value right there. Just in case you couldn't see it. Absolute value of f of 1. Well, f of 1 I think was 0, yeah, so that's just going to stay at 0. This is absolute value of f of 2. Well, I was already positive anyway. There was absolute value of 1. That just stays as 1. And then the absolute value of f of 3, which I believe was 0, so just 0. So just plug those points, 0, 1, 1, 0, 2, 1, 3, 0. And then connect them. What changed compared to the original? Everything that was below the x-axis got reflected. Yeah. Everything below x-axis got reflected. I don't know, maybe you want to say got deleted and then reflected, or reflected and then everything that was below got deleted. But there it is. Whatever was below the x-axis just got reflected above. That's it. Not bad, right? Okay. I mean, this is not really the one that I really want to focus on is letter D and E, but let's just go through all of them since we already have them here. All right, letter B. We have the absolute value inside the x here. So I'm going to go x, f, absolute value of x, negative 3, negative 2, negative 1, 0, 1, 2, 3. F, absolute value of negative 3 is just going to be, absolute value of negative 3 is just 3, so this is f of 3. And f of 3 was 0. Settle. Negative 3, 0. Bam. Does everyone see where I got that? No? See how it says absolute value here? So I got the absolute value of negative 3. Absolute value of negative 3 is 3, and then I went to the original. And look, it tells me that f of 3 is 0. F, absolute value of negative 2. Absolute value of negative 2 is 2. And f of 2 is 1. So negative 2, 1. F, absolute value of negative 1. That's f of 1. And f of 1 is 0. Does everyone see where I'm getting the numbers from, guys? Okay. This one's absolute value is 0, which is just 0. So f of 0 was negative 1. So 0, negative 1. And then these are going to stay the same. Absolute value of 1 is still 1, so it's going to turn to f of 1. F of 1 was 0. Absolute value of 2 is still 2, so f of 2 is 1. And then absolute value of 3 is still 3, so f of 3 was 0. So 1, 0, 2, 1, 3, 0. What happened? What happened, guys? Delete it? Yep. Everything in quadrants 2 and 3 was deleted, semicolon. Quadrant 1 and 4 reflected across y-axis. Cool. I have a slight headache. I'm not sure where that came from. It just came all of a sudden. Yeah. I think I can delete all the little side things. Yeah, there we go. Does that look better? No? That looks better. What's up? Yeah. Yeah. See this right here? I don't have this. It got deleted. See? It's not there. I just have this reflected across the y-axis. See? That's it. So everything that was originally in quadrant 2 and 3 is out, and whatever I had in quadrant 1 and 4 just got reflected. Do you see it or no? I mean, there might be a better way to describe that. Do you see that, Henderson? Or
yeah, I just saw it because you pointed it out, but I didn't get it.
Yeah, we're comparing it to the original. The original being this guy.
Oh, the one on the back?
Yeah, the very first one. You know what I mean? So you're comparing it to that. Like, oh, what happened compared to the original? Oh, well, whatever was in quadrant 2 and 3. Well, I guess there was nothing in quadrant 2 initially, but whatever was to the left of the y-axis got removed, and whatever was to the right of the y-axis got reflected across the y-axis.
Wait, can you go back to the lowercase
Lowercase
a?
a. So what happened there? Everything below the x-axis just got reflected. Are you cold? Like super cold? Sorry, guys. I guess I'll turn off one AC. Just this one. So now it won't be as cold because it's just this one. Yeah. What? You just put in a 1. F of 1. F of 1 was 0. That's the value of 0, just 0. F of 1, F of 2. And it's the absolute value of 0. So that's the value of 0, just 0. That's the value of 1. That's the value of negative 3. That's the value of negative 2 is 2. That's the value of negative 1. All right. Yeah, hit me, guys. Hit me. I mean, not like hit me, but like, All right, here we go. X and then f of negative x. So that just means opposite signs. That's all it means. Negative 3, negative 2, negative 1, 0, 1, 2, 3. Okay. Opposite of negative 3 is 3. So this is f of 3. And f of 3 is 0. Negative 3, 0. Points. Opposite of negative 2 is 2. And f of 2 is 1. I'm referencing the original. Yeah, f of 2 is 1. I'm referencing this one, guys, the original. So opposite of negative 1 is 1. And f of 1, I think, was 0. Yep. This one stays the same. F of 0 is negative 1. Excuse me. F of negative 1 is negative 1. F of negative 2 is negative 2. And then f of negative 3 is negative 3. Plot those points. Negative 3, 0. Negative 2, 1. Negative 1, 0. 0, negative 1. Bless you. 1, negative 1. 2, negative 2. 3, negative 3. What happened? Yeah, everything reflected. Yeah, I guess you could also say rotated at 0, negative 1, but that's fine. Everything reflected across y-axis. I believe that's what Mr. Quinones will probably tell you when you do this one, or if you take some type of algebra course and they tell you what happens when you do f of negative x. All right, this is what I really wanted to look at, this one here. So check this one out. X, f of half x. Let's see. Negative 6, negative 4, negative 2, 0, 2, 4, 6. Child, why are you doing that? Because there's a half in there, guys. I guess I could have done the negative 3 in there, but then I would have gotten negative 1.5, and I don't have negative 1.5. I mean, I guess I do technically, but I don't want to look at it. So look, f of negative 6 times half. that is f of negative 3. And f of negative 3 is negative 3. All I did was put in that x, guys. So if I put in the next x, negative 4, what is half of negative 4? Negative 2. And f of negative 2 is negative 2. Half of negative 2 is negative 1. And f of negative 1 was negative 1. Do you guys see where I'm getting those values? F of, well, this is half times 0, so it's still going to say 0. F of 0 is negative 1. Half of 2 is 1. F of 1 is, well, I don't remember. F of 1 is 0. Half of 4 is 2. And f of 2, I believe, was 1. And then half of 6 is 3. And f of 3 was 0. Let me make sure. Yep. All right, plot those points. Negative 6, negative 3, point. Negative 4, negative 2, point. Negative 2, negative 1. 0, negative 1, 2, 0, 4, 1, 6, 0. What happened? Yeah, what is that? Perfect. What type of stretch? Horizontal or vertical? Horizontal. Horizontal stretch. By what factor? Definitely not half. 2. By a factor of 2. Notice it's a reciprocal of that half. So hopefully we're not robots anymore. Ya no somos robots. Rango bango tam.
Wait, did we only use, did we only use -6 and -4, -2, because that's like what the graph is?
I mean, I could have used negative 3, but then I would have multiplied it by half, and I would have gone 1.5, and then I would have to look at like negative 1.5, and I guess I could have. Negative 1.5 looks like negative 1.5, you know, but I just use those because those are the values that I have here. All right, here we go. This one here is f of x minus 1. So I'm going to start this one. Let's see, x minus 1. I'm going to start this one at negative 2. F of x minus 1. Negative 2, negative 1, 0, 1, 2, 3, 4. F of negative 2 minus 1, that's f of negative 3, which happens to be negative 3. So all I did was plug in a negative 2 in there, and I subtracted 1, so it turned to negative 3, and then f of negative 3 is negative 3. So if I plug in a negative 1 in there, negative 1 minus 1 is negative 2, and f of negative 2 is negative 2. If I plug in a 0, like 0 minus 1 is negative 1, and f of negative 1 is negative 1. If I plug in a 1, 1 minus 1 is 0, and f of 0 is also negative 1. If I plug in a 2, 2 minus 1 is 1, and f of 1 is, I already forgot, f of 1 is 0. If I plug in a 3, 3 minus 1 is 2, and f of 2 is 1. And if I plug in a 4, 4 minus 1 is 3, and f of 3 goes back to 0. Plot those points. Negative 2, negative 3, point. Negative 1, negative 2. 0, negative 1. 1, negative 1. 2, 0. 3, 1. 4, 0. What happened? Yeah. Shifted right once. So that's why every time you have a parenthesis like that, x minus 1, x minus 2, x minus 3, that does a horizontal shift, guys. Cool, right? Okay. I think we're good. I know that was not like, maybe that was not the most exciting, but now we're about to get to exciting stuff. Y'all ready? I'm recording everything, so you'll be able to. Hold on, guys. Something's going on. Okay. Y'all ready? Here we go. I don't know if you recognize this one. This one's actually from your notes. And I went back to degree modes. We're going to start figuring stuff out, like how to graph cosine and sine. This is the midline, the 8. The 3 is the minimum. The difference between 8 and 3 is 5. So I'm going to go 5 up from 8. So I'm going to say that's what, 13? 13. You don't have to do the sound effects. This is a quarter of a cycle. What percentage is a quarter? So from the midline to the low is 25%. So this is 7-degree gap. So that means I'm going to go 7 degrees back. So I'm going to say here's 10 degrees. And I'm going to put a point at the max. And I'm going to go another 7 degrees back. 3 degrees. And I'm going to put a point at the midline. I'm going to go another 7 degrees from the 24. So I'm going to say like right here. That's what, 31? 6, 7, yeah. 31 degrees. And I'm going to put a point back at the midline. And I'm going to go another 7 from there. So what's that, 38 degrees? And I'm going to put a point at the max. And then you know what we do. Yeah, it looks pretty good. Probably one of my best works. We said, what do we know right now? We just know cosine. Y equals A cosine B, parenthesis, actually big parenthesis before the B. X minus C, close, plus D. Nothing crazy. The midline is the D. D seems to be 8. The next easiest one is probably the amplitude. The difference between 13 and 8 is 5. Let's see, what's next? The C. If we're using cosine, we're looking for a peak. Where do I have? Where's my first peak at? 10. So 10 to the right. Or you can just say 10. And then the B, because we're in degree mode, this is 360 divided by the period. So 360 divided by, and I guess I'll write the period over here, period. Let's see, I have a peak at 10 and I have another peak at 38. So 38 minus 10, that's 28. That's not the only way you could have done it. You could have said 7 degrees times 4. That also gives you 28. Or you could have done point of inflection going up, boop, to a point of inflection going up. Boop. 31 minus 3 also gives you 28. So look at all the different ways you can do it. So 360 divided by 28. And I believe this was a fraction. Let's see. 360 divided by 28. Enter math. Don't ever do the decimals, guys, unless it stops immediately, like 12.8 or something. But if it keeps going like that, turn it to a fraction. So you can get perfect. 90 over 7. So 90 over 7. So my equation, y equals 5 cosine 90 over 7, open parenthesis, x minus 10 degrees, close, plus 8. Are we okay? All right. I want to make sure that we're not robots. Remember that I told you that this guy right here tells you your horizontal dilation, 90 over 7? Okay, guys, check it out. It works. This is why we got the formula. So here we said that this was a horizontal dilation by a factor of 2. We took the reciprocal of this. So check it out. If I take the reciprocal of this, where are you? If I take the reciprocal of 90 over 7, I bet you when I multiply it by 360, I'll get 28 degrees. Chop, why? 360 is the period of my parent function. So if I multiply by 7 over 90, that's a dilation. So check it out. If I go 360 times, and I take the reciprocal, 7 over 90, I bet you that's going to give me 28. Well, it has to, right? Because look at that, 28. So guys, don't be a robot. Make sure you understand. It's the same thing as when you were in algebra. Are we okay, guys? All right, here we go. I think we're good. Go to the next page. Don't worry, we're almost done. We're almost done, guys. Equation we came up with in class. This is the same graph. Y equals 5 cosine 90 over 7 x minus 10 degrees, close, plus 8. That's the one we came up with right now. Matter of fact, I'm going to put that one in my calculator because you're not going to have Desmos when you take your exam, guys. So I'm trying to get used to your calculator. So go to Y1, and I'm going to type that in. I'm going to type in 5 cosine. So I'm going to go 5 cosine 90 over 7, alpha y equals enter, 90 over 7, open parenthesis, x minus 10, close, plus 8. Does everyone have that? Your mode's in radian mode. I just noticed my calculator is still in radian mode. What mode should I be in? So click on mode, and then just go here, and then just push degree. Now just go back to your y equals. Now it says degree, see? Everyone okay so far? Okay, click on window. And let's see, what's my smallest window? My smallest x value is 0, so I'm going to put 0. My biggest x value, let's see, 38, 39, 44, 1. I'm going to put 41. It's going by 7, but you don't have to go by 7. X scale, I'm going to say by 10. Y min, what's the smallest y value? The smallest y value is 3, so I'm going to go below that. I'm going to say the x-axis, so I'm going to say 0. And Y max, the biggest is 13, so I'm going to go a little bit higher than that, so I'm going to say 16. Y scale by 1, that's fine. Graph. That's you. We're almost done, guys. We're almost done. You okay, Lara? All right. You can put 8 on Y2 if you want to see the midline. I see some of you have that habit. That's good. 8. There's my midline. Watch. Check it out, guys. Push trace. I'm going to push 3, and I better be at the midline. So 3, enter. Yep, I'm at 8. I'm going to push 10. I better be at the peak. 10, enter. Yep, I'm at the peak. 13. I'm going to push 24. I better be at a min. So 24, enter. Yep, I'm in a min. There it is. Are we okay? All right, here we go. Let's see what this says. Because we're about to do... All right, here we go. All right, guys. So it says cosine with a phase displacement other than 10 degrees. So they want me to use cosine again, but they do not want me to use 10. All right, well, if I'm using cosine, that means I can use a peak. Where do I have another peak? So this must be y equals 5 cosine 90 over 7 x minus 38 degrees, close, plus 8. And that's what I'm going to type in, y3. Y equals, go to y3, 5 cos alpha y equals 90 over 7, open parenthesis, x minus 38, close, close, plus 8. I'm going to push enter. So my graph is the black one. Let's see. Enter. Bam. Yep. It's the same graph. It outlined it. Cool, right? I'll wait for you guys too. You guys get it? Okay. All right. Everyone put your pencils down. For the sine graph, whenever we did the notes, this is the first time we're doing sine. This is a side note. Guys, just listen right now, guys. When we did sine went through the origin like this. Do you guys remember? Yeah. So look, here it is. Yeah. Look, I'll take it out. Open device. What notes was it? Notes. Oh, that's calculus. All right, here it is. Remember when we did this? Wait, yeah, there it is. Look, guys, when we did sine, I want you to notice that sine goes through the origin. Do you guys remember that? Sine goes through the origin. So that's what I'm looking at. I'm looking at that point. I'm looking for a point of inflection on the way up. So looking at this graph here, where do I have a point of inflection going up? At 31 and also at 3. That's the point you got to use for your C value if you're using sine. So if I come over here, I'm going to write y equals 5. Everything else is exactly the same. Sine 90 over 7, x minus 3 degrees, close, close, plus 8. So that's what you're going to type in into your calculator. That's the only difference between sine and cosine. For sine, you use a point of inflection going up. So, boom. Okay, now you can lift the pencils up and start. 5 sine 90 over 7 x minus 3, close, close, plus 8. I push graph. Notice that's in pink. And there it is. Super fast. So what's the major difference between cosine and sine? For cosine, the C is a peak. For sine, the C is a point of inflection going up. Not a point of inflection going down, but a point of inflection that's increasing. Does that make sense, guys? You gotta remind me, miss. I'll look for it right now, miss. All right. You guys ready for the cosine with a negative vertical dilation? All right. So again, put your pencils down real quick, guys. Just listen right here. When it says negative vertical dilation, it means this. It means y equals, let me go. Don't worry, I'm going to give you guys time to write, but just right now, just take this in, just observe. Y equals negative a cosine b, parenthesis, x minus c, close, close, plus d. That's what negative vertical dilation means, that it wants to have a negative in the front. So here's what I'm going to do. Here's a hack. I'm going to write the word hack. And don't just listen. So if I were to make the max a min and the min a max, and I were to plot that, you see this graph in red here? If I were to tell you, give me that equation for the graph in red, you would, and to use cosine, you would say, oh, okay, well, let me use cosine. I'm going to use this 24 here. And you're going to go y equals, everything else is exactly the same. The amplitude's the same. The frequency's the same. The period's the same. So y equals 5 cosine 90 over 7 x minus, what's my peak at? So x minus 24, close degrees, plus 8. And that there it is. That's my, let me make that 24 better. 24 degrees. And that's my equation for the one in red. Yes or no? Yeah. That's my equation. That's the correct one. If I put a negative in front of that 5, remember what that negative does. It reflects across the x-axis. Yeah, I know we shifted it up. So what that negative does is it makes the maximums a min, and it makes the mins a max. Does that make sense? So if I put that negative in front there, that red line will turn into this green one. Does that make sense? And that's the one I want, the green one. So this one here, when it says negative vertical dilation, the equation is y equals negative 5 cosine 90 over 7 x minus 24 degrees plus 8. Sorry. All right. You can write notes down, guys. Put what we did, put the hack, that we got the equation of that red curve, and then we put a negative in the front to turn that positive into a minimum, to turn the max into mins, and turn the mins into max.
Why is it 24 degrees instead of like, what was it up here? 10 degrees?
Well, if I put 10 degrees, that's a minimum. If you're using cosine, you got to use the max. You know what I mean?
Yeah.
For this one, for the one in red, you always use a max for cosine. And then when I put the negative there, it turns that max into a min, which is the graph that I wanted. You know what I mean?
I'm sorry, which graph are we like?
We want the green one.
Okay, we want the green one.
We want the green one. But what I did was I got the red one first. And then what happens when I put that negative there? It turns the max into a min because it's like reflecting. You know what I mean?
Wait, so like, I'm pretty sure they gave us the green one, right? But
This is the green one. This is the green one. This is the green one. We want the green one, but we want it with a negative vertical dilation, with a negative in the front. If I take out that negative, I get the red one. But if I put the negative, it turns that red one into the green one. You know what I mean? We're graphing the same curve. So on the calculator, check it out, guys. On the calculator, go ahead and type it in. Negative 5 cosine 90 over 7 x minus, and I already forgot, what was it? 24 plus 8. And look, it's this green one here. By coincidence, it's green here on this one. And check it out. It's the same. Cool, right?
I thought I wanted to do the opposite though.
No, it wants the same graph. It just wants it with a negative in the front. You know what I mean? They're asking for the same graph. They just want a negative in the front. Letter D. Sine with a negative vertical dilation factor. So they want sine, but with a negative in the front. So look at the red graph. Look at the red graph. Look for a point of inflection on the way up. And then so this red graph, I want it, give it to me in terms of sine, the red one, just normal. 5 sine 90 over 7, open parenthesis, x minus, where's the point of inflection going up? 17 degrees, close, plus 8. All right. I'm waiting for you.
I'm sorry.
No, you're good. No, you're good. All right. See that point of inflection going up? When I put the negative in the front, that red graph is going to turn into the green one. So there it is with a negative in the front. That red one turns into that green one. That's the one I want. Y equals negative 5 sine 90 over 7 x minus, I already forgot, 17 plus 8. So there it is. Let me zoom out so you guys can see. Good. All right. I'm going to go to my graphing calculator, guys, and I'm going to type that in. And I'm going to make sure that all of them are the same. Negative 5 sine alpha y equals 90 over 7 x minus, what was it, 17? And there it is, guys. All of them are the same. Isn't that cool?
So the other sign that we did, the base displacement was 3. So can it also still be 3? Or do you have to do the negative?
No, if you put a 3 with a negative in the front, you're not going to have that green one. Look, you see the y4, I have that x minus 3. If I put a negative there, that's the whole point that we're trying to find out with a negative in there. If I put a negative there, look at y4, it's gonna be out of phase. Look, it's out of phase. See? So what did we do? What was the hack? Let me delete. The hack that we did was I graphed the one in red, and then I put a negative and used my algebra transformations. When you put a negative in the front, the max turns to mins and the mins turns to max. So that one, when I put a negative in the front right there, that that red curve turned into that green curve. You know what I mean? So that point of inflection going up turned into a point of inflection going down, which is what I wanted. That makes sense? Does all this make sense, guys? Was it explained clearly? All right.